And I have started the audio as well, just in case. Um, let's talk about reverse engineering programs from a dead stop, right? So let's say that you are working at a untoward employer and you've got a client and the client says, I want you to find a bug in this very well-known program that is very large and complicated. And where do you start and what do you do and how do you think about it? How do you go from nothing to understanding the whole thing? Okay. So there's a set of steps. Let me take notes while I talk here. There's a set of steps that you go through in order to do that. And the first one is that you understand the point. What do I mean by understand the point? Well, the person who wrote that program that you're going to attack, that program does something, right? Like it has a goal in mind and it has to solve that problem in whichever way it does, right? So if you understand what the program is doing, you don't come into a program blind saying, oh, I got this binary. I have no idea what it does. That's something that sometimes happens in a CTF, but it doesn't happen in real life because no one wants to hack a program that nobody knows what it does. Someone's running the program, they know what it does, right? They have a use for it, right? And so your job very initially is to understand the problem it's solving, right? If you can understand the problem that the program is solving, then you can figure out how would I build it, right? And the more programs you look at and the more programs you write yourself, the better your understanding of this process becomes. But even from the jump, you are computer scientists, you are grad students, you have written some programs, you have looked at some other people's solutions to problems, you understand data structures and algorithms, and that's how all problems are solved, right? They are conglomerations of the types of data structures and the types of algorithms that you know, and they all will be this way, right? They're just some combination of it, right? And so when you look at the problem that's being solved here and you think about how you're going to build it, you're going to think out an architecture, right? You're going to say, what are the problems that need to be solved? They're X, Y, and Z. There's three problems that need to be solved here. I got to take input from the user. This is a network program, let's say, that takes input from a user. It's going to use some set of library calls to do that. It's going to take that data, transform it, and then it's going to act on it and in a particular way that you should understand if you understand what the program is. And that will come with a set of problems. So when I say problems, what I mean is problems the architecture it has to solve. So if you are writing the program yourself, you're going to say, okay, the three hard problems in writing this program are A, B, and C, and I have to solve them. And the ways that those types of problems, I have seen them solved, might take a couple of different forms. So you can think of how you would solve the problem, and you can think of ways that have different trade-offs, right? You think about what sorting algorithm am I going to use? Am I going to use a tree that I'm going to traverse to find something, or am I going to use some sort of array that I'm going to sort on entry so that I never have to search? I basically kind of know where stuff is. Am I going to trade off CPU for memory or memory for CPU? That's always a trade that can be made, right? And those things have upsides and downsides. All of those solutions have upsides and downsides, and people are going to choose different ones for different reasons. But you can basically identify what type of solution there is. So when you come into this reversing at a high level, you should know kind of how you would build the program and kind of what problems the builder of the program had to solve. And so your job, if you don't really understand what's on in this program, is to identify what solutions they chose, right? So, right. And that gives you uh, a framework to understand what the program is doing at a high level. You don't have to reverse engineer step by step to come up with these answers. You can jump around a little bit and say, well, uh, all I need to know is enough about what I'm looking at to recognize the solution to this problem. Okay, so even that is pretty vague and doesn't really tell you how to start. So one of the best places to start are something we just looked at, which are library functions, right? I can pull up IDA and I can look at the imports, and I know things about puts in A to I, right? Those are known library calls. They have man pages, and even better than having man pages, they have types. Okay. Reading assembly is not the number one way to reverse engineer a program. Uh, Figuring out and defining structures and classes is the number one way, right? Um, Now, why is this? This is because a program's interaction is primarily structures and classes and library functions. In isolation of all the other code, if we know the structures and classes and what their types are inside, and we know what the library functions getting called are, we can basically guess what a program does. And structures and classes will help you define functions and understand functions very, very easily, right? If you are looking at a function, we look at uh, the problem that we primarily have is if we don't know what these arguments are, we've got nothing to go on except for the library calls. But if we know what all the arguments to a function are, we can see them throughout the program. We can be like, oh, that's argv. I know what argv is, and I understand, therefore, exactly what's going on here because I understand argv, right? And so if you go through your types in your disassembler, any good disassembler is going to have a type structure that allows you to create C structs, right? And even classes in C++, you're going to create them as C structs. And then I'll show you very soon what differentiates a class from a structure and how they kind of sit together. But at a base level, they're just structures, right? They're just complex sets of types that live in memory. Okay. And so if you understand this here, and you can name all of these things and you can give them a type that then when you go to look at the assembly, it makes a whole heck of a lot more sense to you. And so, especially if you have something that's got a decompiler on it. So is it F5? Is that what I want? F5? Nope, no, that's not it. Function F5? Yes. All right, cool. And then what I'm going to do is put it next to the assembly. And I'm going to link it to the assembly. Okay, so now that I've kind of linked those two, I did synchronize with, uh, it'll show me what it thinks the C line is that goes with the assembly, right? And so often when I'm reverse engineering, I'm looking at it in this way. reading the assembly, but I'm also kind of saying, okay, and it identifies the whole block of the line, which is how I want you to think about uh, doing reversing of assembly. And we'll get there in just a second. But let's see, where was I? Oh, yeah. Okay. So types. Once you understand the types, it makes this disassemble section here extremely readable, very, very readable. And you can basically uh, comment out a whole program if you just know what the types are of the arguments of the program. And so uh, you will start off kind of sparse on your types. Now, if we don't know anything about the types, how do we start off figuring out what they might be? And the answer is we always start from our imports. So if I'm trying to find a remote bug in a program, let's say it's a web browser, right? And it's a custom web browser, it's a small one, and I want to find a bug in it. I'm going to go to the imports and I'm going to look at read, which is going to read data from the network. And I am going to read the function that reads the data from the network. That's where I'm going to start. Every one of these imports, I will select ones that I feel are interesting, and I will start to branch out from there, especially library functions that have strong types associated with them. So on Windows, there's a lot of NT calls that take these big structures that are related to system data, right? Like you're going to call a function and ask this function something about the state of the operating system, and it's going to give you back this big structure that's got a bunch of types in it and a bunch of data, right? And so that will allow you, by looking at what's pulled out of the structure, the data type that you know, because it's defined in the man page or on MSDN, you can then use that to say, okay, I see it being added to this internal structure of a type I don't understand. Now I can transfer those types from what comes out of the known stuff in the library calls into my unknown data structures and start to build them out. And so that is how you start to build up an understanding of those types. And then you can trace pointers to those types through function calls away. You are branching out from those import libraries, right? And saying, okay, um, I understand a piece of this internal structure because I pulled it out of this library call. Let me trace that through function calls and through the assembly and see if I can identify what the other pieces are. Probably they will be referenced to pieces that are already in there or from other library calls. They will be transformed in some way that you can reverse, and then they'll be stuck in there. Or they will be referenced someplace else and used as inputs to a library call. And that will tell you exactly what the type is because you will always know what the type of arguments are to a library call, right? So return values from library calls and arguments to library calls give away types that you can then use to identify the structures that are inherent in the program that you're looking at. Once you have done that and built up those data types, you can use that to reverse engineer the rest of the program. And so that kind of gives you a place to start and then go back to your understanding the point, right? Now that it becomes much easier for you to identify and work through your types, you can go back up and identify the solutions to those problems. Once you can identify the solutions to those problems, you can use your experience and your understanding of what problems are hard and what problems are easy. You can say, in times that I have looked at these types of programs before or tried to solve this problem myself, how have I screwed up? Right? You can think about what's hard. Where have I seen bugs? Where have I screwed up writing code? And then you can go and look specifically at those places, right? Having identified the solutions allows you to do this. If you have not said, okay, the problems this program needs to solve are X, Y, and Z, and the way that I could solve it is A, B, and C, then you will have no place to understand what's complex. And so you won't know how to prioritize what you want to look at when you're bug hunting. But if you have seen a lot of bugs, then you will be able to identify trouble areas. So the other thing that you need to do here, and this is like kind of like a pre-step, is look at a lot of bugs. You should be looking at historical bugs, things that are in Metasploit that have solutions that you could then reverse engineer yourself and understand how you would have solved that problem and understand how somebody else solved that problem. And you are going to get a bunch of examples. You should look at bugs that come out now as well, but you're going to get a bunch of examples of places people screw up, right? They always screw up the same stuff. The same stuff is always hard. So get a pattern matcher in your head, build some meat space machine learning around where people screw up and what the consequences of those screw ups are and what it looks like when those screw ups happen so that you can identify kind of at a crash time what kind of screw up is this likely and how likely is it to be useful to me, right? So that's kind of how I think about tearing down a problem in the abstract, right? That's how I come about bug hunting and reverse engineering large programs. That's my thought process. Now, how about when you get really in depth and you say, all right, I got to figure out what these structures, these types are. I've got to figure out what this code does. How do I think about the code itself? Now that gets a little dirtier, but if you remember how I tore apart this code previously, I said, all right, this here, this is the preamble, right? This is the preamble. It always looks the same. And in this in IDA, if I click on main here, it's got argc and argv and oh, and look, it shows us NP. We talked about that earlier, right? So even though the C doesn't specify it, it's still there. It's still going to be that third argument. It actually shows us the function preamble. It's like, yeah, this part here is what goes with that function start, right? The next part I'm thinking about is I'm going to break it down even more than this line of C. I'm going to say, here's the call to A to I, right? That's another logical block. And that logical block is you pull out the argument, you push the argument to the stack, and you call this function. And we'll put this in here too, the stack fix up, right? So if I'm going to draw this out, I'm going to break these up into two blocks. IDA does not do that when it shows you a graph view. Let's go back to graph view for a second, if I can. No, that's not it. Where is it?
Doesn't it just turn on if you hit space?
Is it? Yep, you're right. Thank you. Excellent. Yeah, so this is not showing blocks in the way that I would do reverse engineering. This is just showing, it only shows block differences as branches, right? So yes, these branches you should break out as blocks because they're logical blocks, but you should break it down farther than that, right? You should be breaking it down into logical thought processes and understanding each piece of that, right? So not just, okay, it does these things until it branches, but why does it do this thing? This is a single thought. This is a single thought. This is a single thought as a C programmer or a programmer of any language, right? Um, and so when we assign, we're going to do the lab the next class, and I'm going to assign you guys an extra homework, and that extra homework is going to be write a doubly linked list in C++, use classes to do it, and then you are going to do a breakout of the add and remove functions that you wrote. And you're going to break them down into blocks like this. And so I kind of want to see this graph view, but I want to see it broken down into more blocks. Each block is going to be uh, this logical piece. And then you're going to write a comment next to that logical piece that says, this is what's going on here. This is why it does it in this way. This is why the compiler made these choices, right? And the goal here is to start to train yourself not to read instruction by instruction, but to be able to read block by block, to be able to take a look at what looks like a wall of assembly instructions and read them as English words instead of reading English letters, if that makes sense, right? And the only way for you to be able to do that is to do it a lot. And so we're going to start with that doubly linked list because it's a something you will see in every single program your entire life. There will never be a program that does not have linked lists unless something happens with quantum computing that I don't understand. In which case, there probably will still be a lot of computers with linked lists, right? So that's a good one to start with. But um, you're going to be following basically the same thought process and premise that we did when we looked at branching, which is I don't necessarily understand how this thing works. How do I solve that understanding? Well, what I do is I write it in a language that I understand, and then I compile it, and then I break it down. I break down the compilation until I understand and can guess what the compiler will do when I write certain C code. Does that make sense? I think it does, so I'm going to assume so.
Yeah, that makes sense to me.
Cool. I will write up a more specific uh, set of instructions on how I want you to do that exercise that will be provided next class. But that's how you should be thinking about this, right? You're learning to just breeze over chunks of assembly and say, all right, I understand what that one's doing. That's loading from argv. Okay, I understand what this one's doing. Okay, here's how there's a loop in here, and here's how the loop works. And here's where the conditional is checked, and I understand pretty much what this conditional check is looking for. And you get a solid understanding in that way, right? But uh, at a higher level, it's all coming out of information that we natively know, which is how library calls work. Every program is going to have library calls. If it doesn't, then you're probably looking at a piece of malware or a piece of firmware. And in that case, firmware will be interfacing directly with the hardware. And the hardware is going to have its own documentation. And so then it will be on you to identify where the software interfaces with the hardware and work backwards from that. Because even hardware will provide you structures that make sense, right? What else do I want to cover with you guys for this? Um, yeah, so in between now and the next class, you're probably going to want to select a disassembler that you're going to use for the rest of the class, and that can either be IDA or Ghidra. You can use Binary Ninja. Um, that would be my last choice. So IDA or Ghidra, if you're going to plan to learn Windows things or want to learn Windows things, or you're particularly serious about this, I would get IDA. That's what most of the high-end people of my generation are still using. Ghidra is relatively new industry-wise. I don't expect it to go away. I expect it to probably be to become at least as powerful as IDA over time and probably as well used. So either of those would be a good choice. Select one and kind of get comfortable with doing the things that we did today in the undergrad class with your disassembler of choice. So by that, I mean go through and look at the segments and understand how it lists out the data on those segments. Go through and look at imports and exports. Load up a program that you don't know about at all and poke around and get comfortable with those three pieces. If you're looking at Windows, and you're using IDA, uh, open up NTDLL and actually get the symbols, have IDA pull the symbols down from the Microsoft symbol server and look at the types because it'll give you a lot of native types. look up those types on MSDN and see what the documentation says, and then look up the types in IDA as the debugger provides them to you, um, and kind of make a match between those things and understanding there. I would also suggest that you find some instructions you don't understand, put your hex view next to your code, and then do something like this. Say, okay, I don't understand compare, but in my hex view, I can see that 81 is the first byte on this compare, right? So then if I go over to compare here in my manual, I know exactly what line I'm looking for. It's this one, starts with 81, right? So now I can actually look up in my table by the opcode. These numbers here, which are static per instruction, are known as opcodes or bytecode. Um, this is a native bytecode, so it's the bytecode that the processor speaks. Bytecode can also be virtual machine native. So, like if you're compiling Java to be run in the Java virtual machine, it's still compiled to bytecode. It looks like this, and it's going to act in the same way. There are instructions that the Java virtual machine understands, but they're not the same as what your processor understands, and they're going to have different types of things associated with them. But that's still bytecode. Um, there is also such a thing as JIT compiling. Has anybody ever heard of that?
Yeah. Python
Yeah.
313.
Yeah, JavaScript is often JITted, which means that it will be compiled at near runtime into native code. So even though it's a scripting language, it's still going to run as native code, right? And that gives you some interesting opportunities where you have pages that are going to be writable and then subsequently executable immediately afterwards. And so you can kind of race that sometimes if you've got a good write. Anything else that I want to cover before we get into the lab and I provide the homework to you guys? Um, I'm still contemplating if I'm going to give you a second program to exploit along with the reverse engineering stuff. Uh, Probably what I will do is I'll give you the reverse engineering assignment with the undergrad exploitation assignment and nothing else right now. And I'm going to want to gauge for how much time it takes you to do that doubly linked list. And then from there, we'll probably add extra assignments going forward. Um, as I said when we met kind of at the end of last class, there's a lot of leeway on how we focus the graduate section. So I'm going to want feedback from you on where you want to work more and where you're not interested and what you know and what you don't know, because that's going to be very different from what the undergrads know and don't know as well. So um, I like this to kind of function as somewhat more of a seminar rather than like kind of lectures. Unfortunately, this was a class where, we didn't have campus, but normally the way that I would do this would be we will all sit around in a circle and so you would all be working on your laptops while I'm working on mine, and I'll provide kind of more hands-on stuff and we'll talk through it. But this class, of course, was necessarily more of a lecture. Does anybody have any questions? Nope. All right, cool. I think you're going to be prepared for the assignment. I'll give you a solid write-up on it. But I think we should call it for the day. I got to go drive someone to Boston to the airport. But I will see you all next Tuesday for our first lab. Everybody should have a VM or a shell by then, hopefully. And if you don't, make a ruckus. Everybody
Wait,
good?
I
Thank
ask
you.
something quick last minute.
What's up?
Do you know when the SSH machines would be set up for the remote people trying to SSH in?
Boy, I hope soon. Cybersecurity Club is handling for that for us, and one of the problems they're having is being able to route the IP they've got for the server to you guys. So, if worse comes to worse, I will make a cloud server on AWS, and we'll make it happen. But hopefully, it'll happen before Tuesday.
Okay, sounds good. And then when we're like trying to work with Ghidra for that, is it just a case of just me just transferring files locally every time I want to disassemble something, or
Yeah, you'll work with Ghidra locally. You should just use SCP to copy the files back and forth. But I will give you the binaries on Canvas, so you can just pull them straight down to your native machine.
all right.
Uh, the way that I generally suggest working on this stuff, because if you're in real life hacking something, you're always going to do it in a virtual machine. Always, always, always. And that's because snapshotting makes your life much better. Um, but you want to do your development and your disassembling on your native machine, not in the virtual machine or the shell you're attacking, because when you revert the machine, you lose all your work. So, yeah.
Hmm.
Could you do like a lecture on how you like the advantages of doing stuff in a VM versus doing it on your host OS?
Yeah, absolutely. I mean, we can talk about that. I'll Tuesday after lab when we meet again, um, we can go over that a little bit.
Sweet, thanks.
There's something else about that that just slipped my mind, so I'm gonna have to think about it. Something else I wanted to talk over in that vein. All right, cool. I'll talk to you guys on Tuesday. Leon, you want to kill this recording?